Welcome to today's session. Welcome, everyone. Everyone to kindly remind. So we are on the phases of matter using machine learning, how machine learning can be applied in physics, and to explore different phases of matter. So please join me in giving a warm welcome to Mohamed, and let's make this session productive and insightful. Thank you.
Okay, thanks very much for the very kind introduction. It's an immense pleasure to be here. Thank you all for joining this session. So today, I hope that I'll provide you with a brief overview about one interesting topic at the intersection of machine learning and many-body physics. So I'll touch upon one area in this research field, specifically about the use of machine learning to classify different phases of matter. Before getting started, I just wanted to note that it's totally okay to interrupt me. Like, you can just unmute yourself and ask your question if something is not clear. And also one thing I wanted to do before getting started is just to get your background on the area of machine learning and statistical and many-body physics. So I wanted first you to participate in this poll. So you can go using, for instance, your phone or your laptop to this link, or you could scan the QR code and type in the code here. And once you get your answer, then I'll be able to see your answers here. I just wanted to know, what's your level of familiarity with many-body physics? Either you could answer, have not seen that before, or either that could be a beginner level, intermediate level, expert level. That'll be very helpful so that I know how fast I should go during this lecture and also in the next lecture. That's good. I got some answers here. That's great. Any other answers? I should also know that this is anonymous, so nobody would know who responded with what. That's good. Okay. So I can see that the majority, yeah, has a beginner level. So that's good feedback. So in this sense, I will make sure that I will go as slow as possible. But if in the meantime, if during the lectures I'm going very fast, please feel free to interrupt me if something is not clear. Okay. Okay, so that's great. That's good. That's good feedback. I also wanted to know about your level of familiarity with machine learning. Can you also do the same thing for this one? I just wanted to know whether I also should go fast or slow when explaining things that are related to machine learning. Okay, that's good. I guess it's somewhat similar. Yeah, that's good. Okay, that's really good. I guess like in that sense, I can maybe start from scratch and explaining how things got started with machine learning. No, this is good. That's great feedback. Thank you. Okay. With that being said, well, let's get started then with this first lecture. I guess, yeah, this is like great feedback. Appreciate it. So for the first lecture, I'm gonna talk about the basics of machine learning. So this will be the main topic of this lecture. I thought that would be great since like it will be hard to cover everything in one lecture related to physics and machine learning. So we'll cover the basics of machine learning that will be necessary later to explain how we can use machine learning to classify phases of matter. Okay. So first thing that I thought would be great to show is this plot from Google Trends, which basically shows like what's the interest over time of a certain like search term. So if you do that on Google Trends for machine learning, you'll see that the amount of interest, which is on the y-axis over time, is increasing like consistently. You can see, for instance, that in particular, if you look at around 2012, you see like some consistent increase over the years. And one reason behind that, I guess, is related to this interesting breakthrough that happened in 2012 related to image classification using machine learning. So this paper, which is famously known as ImageNet, allowed to get top performances compared to other computer algorithms that can automate image classification. So there's this data set called there's that data set, which is ImageNet. In this context here, it's in the abstract if you want to check out more details, which allow to get top performances compared to other state-of-the-art algorithms back at the time. So that was a very breakthrough that allowed to a lot more people to get into this field and to do more investigations. And this also was even more amplified with other breakthroughs, like the one that was made by DeepMind in the game of Go, which is one of the most difficult games known in history, where a computer algorithm have managed to beat one of the world champions in this game. And there's also like a documentary about this in 2017 that you can check out if you want to learn more about this. And this was also like this interest in machine learning was even more amplified with language translation, where this post in the New York Times have highlighted the quality of Google Translation that was enabled using tools from machine learning. And I guess since most of you know that this is like getting like even more interesting with tools like ChatGPT. So for instance, if I ask ChatGPT to explain machine learning in one paragraph to a 5-year-old kid, that actually gives something that's really cool, like that I wouldn't think about if I didn't get an answer from this tool. So maybe I'll give you a few seconds to read how good this answer is. But I guess most of you have tried ChatGPT before and you've seen how amazing it is. And later on, like after 2022, when ChatGPT got released, there were even better releases like that got published later, like GPT-4. I guess this is even outdated. Like might have seen like even better versions that came out in the last few months. And I've tried it myself using this like GPT 3.5 version. So what I tried to do is to scan one copy of my handwritten notes. So these are my handwritten notes in one of my lecture notes that I typically gave. And I asked ChatGPT to say, can you convert these notes to LaTeX? So that's LaTeX, in case some of you don't know, it's just one way to write a PDF documents, and that just looks nicer. And it actually does that very well, except that there are some few errors. So those are the ones that I highlighted in red here. And also there are some omitted parts of the notes, but I guess it's already great because that could save me a lot of time if you want to convert my notes to handwritten notes to digital notes. So I guess that was really a great application of this tool. And another application I want to highlight as well is the ability of machine learning to generate images, starting from just one simple sentence of something you want to imagine happening in the picture. So this is like the prompt that I gave to this DALL-E that you can also try on this link here if you're interested. So I just asked DALL-E to generate a 3D realistic render of an astronaut walking on Mars, and it gave a very impressive answer. I also did that here. So that's a pencil and watercolor drawing of a bright city in the future with flying cars. So you can see here, like maybe that's the flying car. You see also trends of the city of the future. So that was something that was imagined. It didn't exist. And also it kind of also respected the fact that I told DALL-E to use a pencil in watercolor. So that was also impressive. You can also imagine situations that might not exist in reality. So here I asked to generate a tree growing on top of a hand, and that's also was impressive to see. And even more impressive, I also wanted to share like with you this sample, which was generated by tools from machine learning. which was pioneered by this company called AVA, which stands for Artificial Intelligence Virtual Artist. So let me share that sample. I hope you will hear that. Okay, so that's pretty cool. So that's all done by machine learning. So that was also impressive. And something also related to science and math is the following interesting application where researchers recently, just last year, have shown that machine learning can also solve very hard problems. So maybe you have heard of the International Mathematical Olympiad, which have very tough problems that very few people could solve. In this application using an architecture based on machine learning called alpha geometry, they have shown that they can solve very tough geometry problems. So that was something I wouldn't thought about few years ago. So that was really impressive. And now in terms of applications to physics, there is also tons of applications for machine learning. So for instance, there's this one that's related to cosmology, where researchers have shown that it's possible to use machine learning to automate the process of classification between, for instance, spiral galaxies and elliptical galaxies or other types of galaxies. There's also this interesting study which have shown that it's possible for machine learning to discover physical laws. So in this paper, which they call it AI Feynman, so Feynman is one very famous physicist, and they used this machine learning tool they applied it to 100 equations from one set of famous lectures in physics called the Feynman lectures in physics, and they discovered all of these equations. So that was really cool. And for instance, like if you're familiar with special relativity in physics, they have mentioned that the neural network, which is one machine learning architecture, they use that to find the expression of the energy of a particle in special relativity. So that was really impressive. Another cool application is in terms of promoting the ability of computers to discover science. So here in this paper, they have shown that it's possible for a machine learning algorithm to discover new experiments in the context of quantum optics. So that's, you can check out the details if you're interested in this paper. But it's really cool to see that machine learning algorithms could help scientists to discover more science. And it's also within the trend of this research, the same, like one of the same authors showed also that it's possible to use machine learning algorithms to predict the future trend of research in the next 5 years or so. And it does that really very well. So that can also help scientists to discover kind of new areas where to work on in the future. And also, like in the last few years, machine learning has been also very helpful in studying materials and also quantum materials. So this is something still going on, and there's a lot of promising areas in this research. So I just wanted to have this brief introduction just to highlight how cool is machine learning, how applicable it is to a wide range of areas in industry and also in science. So first of all, I just wanted to ask those who have heard about machine learning, what would you think is machine learning? So I have here a Slido link for you to participate. So you can type anything you think you have an idea about machine learning. So just feel free to share what do you think here, and that would be very good. That would be very good to have your feedback before moving on to the details later. So again, this is anonymous, so nobody would know who answered what here. You can also unmute yourself if you want. That's also good.
Okay. Good day. So Machine learning is a branch of computer science that uses mathematical models or algorithms to learn patterns from data and make informed decisions or predictions.
That's a really great answer. Yeah, I guess that captures a lot of what I was hoping to tell you. So this is a great answer. Thank you. Thanks very much. Does anyone have another answer? Yeah, machine learning is also a branch of AI. That's also a great point. Yeah, so that's also what I wanted to share. Yeah, machine learning is promising. Yeah, it's a bunch of algorithmic approaches that uses data. That's cool. Okay. Well, I guess that's also great to hear that some people have an idea about what's machine learning. And so here I have the definition that I found in Wikipedia, which says that machine learning is a field of computer science that uses statistical techniques to give computers the ability to learn and also to improve with data without having to explicitly program them. So that's the takeaway here. We don't need to program them in order to achieve a certain goal. So that's what's cool about machine learning. And also a physicist's definition that I found also is this following, which is that machine learning is about the ability of finding irregularities in patterns in data, which was the answer that was highlighted recently. And it's also about making use of them for fun and also for profit. That was also a cool definition I found. And also in the poll, I've seen like one interesting answer, which is the fact that machine learning is not artificial intelligence. So artificial intelligence is actually much bigger. It's about computers that can mimic the intelligence human behavior. And machine learning is a subset of AI, which is about, again, computers that are programmed to learn without being explicitly without explicit rules. And in this lecture, we're going to focus on a subset and even a subset of that. So we're going to talk about a bit of neural networks. And more specifically, we're going to talk about one architecture in the field of deep learning called the feed-forward neural network. So we'll talk about that hopefully we'll get to that and the amount of time that we have in the first hour. So let's get started. So I'm gonna now share my other screen on my tablet just to see so that you can see my handwritten notes. So I hope you see my other screen. So in the outline for this first lecture, I'm gonna first tell you a bit of the different machine learning algorithms that are out there. This is just for you to be aware of what are the different categories of machine learning, and then we will dive deeper into one specific architecture called the feed-forward neural network. So we'll talk about the architecture. Hopefully, if we have time, we will talk about some other details like related to the architecture and also how we train them. And then in the second hour, so we'll take hopefully like a 10 minutes break, and then we'll reconvene back to do hands-on session on Google Colab, and we'll do like a tutorial so that you can practice on a task which is about classifying spirals later, and that will be using this feed-forward neural. Hopefully that will be enough for material for the next lecture so that you can see how we use machine learning, more specifically these feed-forward neural networks, to classify different phases of learning. Okay, so let's get started. But before telling you about the different ML type of ML algorithms, is there any question so far? Okay, so far so good. So let's get started with the first section on the different ML categories. So the first one that's typically used in the context of machine learning is the so-called supervised learning. or also known as SL. So that's the shorter or abbreviation of supervised learning. And within this context of supervised learning, we typically have some sort of data sets. I'm going to give an example later for concreteness. So basically what this data set has is a bunch of data points, which are vectors. So these could be images, or it could be words, or it could be any types of data that you could have. And we also have labels, okay? So these labels could be, for instance, whether a picture is for a cat or for a dog, or for any other types of tasks. And just to clarify more, this vector x, so each vector x could be a vector with a certain size, where this size is dependent on the context that you have. So dx here is the size, so like is the number of components in x. And we also have a y, which is a label. So this label could be either, so excuse me here, so that could be a vector. And we'll get to the example for where that's a vector. So this dy is the dimensionality of the vector y. So let me write it here. So that's the number of components of y. So typically that y is just one number. So for instance, if we're interested in a task like classification, so y could be a number, not a vector, just 1 and 0. Typically, we use one notation called the one-hot notation, where instead of using 0 and 1, we could use 0, 1 like that, or 1, 0. So that's the case when we use a vector. So you'll see it today in the hands-on session. So that's the case when we have, for instance, binary classification. Or we could also have y like as a real number, for instance. So that's when you want to fit something. So that's the context of regression. So here it's just a number, okay? And just to give you examples, so here I'm being a bit abstract, but I guess it's good to give some examples. So let me share some examples with you. So the first example is 1D regression. Okay. So here I have, again, the data sets where the x is just one-dimensional vector, which is just a real number, and y is also a real number. Okay, so here I can actually plot the data, and so in the x-axis, I just have the values of each different data point, and also on the y-axis, I will just plot the y's. Okay, and I could imagine having something like this. So those are the different data points. Okay, and the goal is to find some sort of function that could fit this function very well. So I could imagine having something like this. Okay, so that's something that we could do in the context of supervised learning. So of course, this is a simple example, which is the context of regression, but you can imagine that this could tend to be more complicated when x is no longer a number, but could be a high dimensional vector. So that's the next example I want to show. The second example is the handwritten digits classification. Okay, so here now I have another example where I have a data set that's made now of vectors and also labels. So now the vectors correspond to images of handwritten digits. So each axis is an image of handwritten digits. And y is the corresponding number. So let me explain what I mean by this. Okay, so what I mean by this is that I could have x to be something like this. So I could have something like that. And then I could write, so I could have something like, so this picture has a bunch of pixels, and then I could write 3 like that. So that's a handwritten 3. So that's the picture I have. And then the label, of course, that label should be equal. So that's a number. So label should be equal to 3. Okay. And then I could also imagine another example where I could have like 2 numbers written differently, like a 7. So, 7 could be either written like this, or I could also write it like this. So both of these should give me a label equal to 7. Okay. So there is an example of this data set already available online. So this data set is called the MNIS data set. In case you're curious, you can check out this data set and see that also you'll find a lot of examples of these data points and their corresponding labels. Okay. So those are 2 examples of what we can do in terms of supervised learning. So the first example is for regression. So that's what we're hoping to do here. And the second example is for classification, more specifically here for handwritten digits. Okay. But if you can summarize everything, the goal basically is to figure out a function. So that's the goal here. The ultimate goal is to find out a function. So that depends on the architecture that we're going to choose later. So we need a function in such a way that this function maps x, which is the data point, to the label. So we want a function in such a way that fx is as close as possible to the label. Okay. And we hope that once we have this approximation, once we generalize to new data points, eventually it will provide us with the correct label. Okay. So that's the main spirit that we're hoping to achieve in the context of supervised learning. Now, there's also the context of another type of machine learning task that you might have seen is which is the unsupervised learning. Okay, so that's also known as UL. And here, basically the main difference compared to supervised learning is that we don't have a data set. So the data set is only made of vectors. So we don't have the labels. Okay, so let me write it here. We don't have labels. And typically we use this when we have some sort of data sets where we don't have an idea about what's the different categories that exist in this data. So for instance, you could imagine a simple example where we only have pictures of handwritten digits and we want to know how many different categories are there. So if you do this, then you would be able to get, for instance, since we have 10 different digits, then we would be able to get 10 different clusters of categories. So that's one possibility that we could have in the context of unsupervised learning. So if I want to summarize this, then that would be the goal of unsupervised learning would be to extract meaningful features from the data set, from the data set D to efficiently represent it in a way that's it's easier to handle. So that's one possibility, like in the context of unsupervised learning. I just wanted to touch upon that very quickly because that's not going to be the goal of the next lecture. But just in case, what I want you to remember here is that in unsupervised learning, we don't have labels, just the data points. And we want to extract some meaningful features of this data set, okay? One final category in machine learning is the so-called reinforcement learning. Also known as RL. So this is something that you typically could imagine when you play games, like when you're playing game, like you have some sort of environment and you want to maximize your score while playing the game many times. So that's basically what's the aim of this feature of this category in machine learning. The environment doesn't have to be a game. It can be any sort of environment. It could be on a game, or it could be like a classroom or a laboratory. So it can be anything that maybe a robot could explore and maximize a certain reward. Okay. So here we don't have a data set. Basically, the robot or the machine learning algorithm would learn by experience. A given environment, we would, like the machine learning algorithm would take actions such that the reward that you get out of these actions is maximized. Okay, so this is, for instance, the goal, like the example of AlphaGo that I've shared with you on the slides. So a part of the training involves reinforcement learning, which is about encouraging the algorithm to take actions to get a reward that's maximizing or that allows to win more games with other competitors. Okay. So given that brief introduction, so now let's go to the second part, which is about introducing one famous architecture in the context of machine learning called the feed-forward neural network. But before doing so, I just want to ask if anyone has a question, I'll be happy to answer. Is everything good so far? Cool. If there's no question,
yes.
then
Hello.
yeah,
Sorry.
please go ahead. Yeah.
Okay. I just wanted to ask the last kind of machine learning you spoke about, the reinforcement learning.
Yeah.
Is it like this example where you go to the internet, you search for something, and before you finish reading, there is a question that pops up. Does that satisfy your search? If they take that answer, somehow they may make the responses or the search findings available to other people. Does it look like
So you're talking about
reinforced learning somehow?
recommendation systems where you're getting things that like based on your previous searches? Is that what you're referring to?
Exactly.
Oh, that's a great point. I guess, yeah, that would be more like that would more fit into like supervised learning, where supervised learning you have some sort of data, like you have some sort of data sets. So either supervised learning or unsupervised learning where you have a history of your data sets, which basically corresponds to your search prompts. And these algorithms basically would use your prompts to generate new recommendations. I guess in the reinforcement learning, it will be like some algorithm, for instance, an algorithm that's playing a game, and that game, like the robot doesn't know the rules, but just get a reward at the end, and the robot will start, or the algorithm will start playing and playing and playing until it figures out a good strategy to win the game, based only on the information on the reward. Does that answer your question?
Okay, thank you. I think that's good.
Hello.
Thanks.
Hello.
Yeah.
And I wanted to know if there's a difference between the self-supervised and unsupervised learning.
So the question is whether there is a difference between supervised and unsupervised?
No, self-supervised and unsupervised.
Oh, self-supervised. Yeah, I haven't like studied that term much, like so but from my understand, self-supervised is that you're getting like the model generates data on its own. Is that what you're referring to as self-supervised?
Yeah, something like kind of like that.
Yeah, I guess maybe that fits more into reinforcement learning, because when let's say you have a robot like exploring some sort of environments, when you get new experiences, it's like you're getting new data about the world that you're exploring. In that sense, it's like self-supervising. You're teaching yourself by experience. But here you get some external data that's already available, like for instance in unsupervised learning, you already have this data available to you. Does that answer a bit of your question?
Yeah, a bit of it. Thank you.
Yeah, but yeah, feel free to follow up later. I'll be happy to learn more about what you meant.
Hello.
Yeah, thank you.
Yes, I have
final
a question.
questions?
I have a question.
Yeah, please go ahead.
So, with regards to the handwritten classification, how is it going to get the, I don't know, because it's an image. So, what concept is it going to go through to be able to predict that this is letter A
Very
or
good.
this is number 7?
Yeah, this is a really good question. And actually, that's what I'm planning to cover in these slides here. Okay. So just stay tuned until I present those slides. But if it's
Okay.
not clear, let me know. I'll be happy to clarify again. This is a great question.
Sure, I will.
Thank you.
Thank you.
Hello.
Yeah, please go ahead.
Yeah, I wanted to ask if there's a way to use reinforcement learning to help supervised learning converge better to optimal solutions or optimal models. Can it improve the convergence timing in some way?
Wonderful question. It's actually a very interesting question. So this is something actually that is done at the training level of ChatGPT. So ChatGPT has two components. There is the supervised portion, and there's the reinforcement learning portion. It turns out that what they found is that when you combine supervised learning with reinforcement learning, you get a better performance. So the supervised learning part comes from human feedback. So the actual humans give feedback to ChatGPT to get even better. So if you would just use reinforcement learning, then you might not get like a good performance that we see nowadays. But with human feedback, you can actually help to converge better. So this is a really great suggestion. It's always possible to combine different categories of machine learning to get a better conversion.
Okay. So it can actually like
maybe shift model parameters slightly, especially if we're talking about like a neural network.
Yeah, this is
Okay.
a really great suggestion. Yeah, thanks.
Okay. Thank you.
Hello.
Yeah, please go
Oh,
ahead.
okay. So what I wanted to say is, if you feed a machine with a data, and there are some changes in the data along the way, like the machine learns more about new data from the data already fed the machine. Is that kind of like maybe self-supervised or maybe unsupervised? I
Yeah.
don't know if that's my point.
So
My point.
yeah, so that's yeah. I guess like you're referring to generalization, right? Is that what you're referring to?
Oh, okay. So there's a generalization of data sets, and the machine
Yeah,
asks.
so that's what yeah, that's a great question. So that's what we're hoping for here. Like, so this is like, if you want to say like this is on the train data,
Yeah,
you also hope that this work also on the new data.
yeah, yeah.
So that's basically called generalization.
Oh,
So that's also a different like a research area in machine learning. This is a good point.
all right.
Yeah, I'll get to that hopefully in the slides, but these are really great questions. I hope, like, I would love to take more questions, but just for the interest of time, I'll go and get started with the second part, which is about feed-forward neural networks. But in the meantime, please like please interrupt me if something is not clear within this section here. So before introducing feed-forward neural network, I just want to give a historic motivation for neural networks. So neural networks have been actually studied since the 70s, so it was a while ago, and they have seen a breakthrough, like as we've seen, like in the introduction in 2012, where there was a breakthrough in the field of computer vision, thanks to this study, which allowed to get interesting performances and better performances compared to the state-of-the-art algorithms back at the time. And I guess you all know, like neural networks, like with architectures like ChatGPT, they're making wonders in the field of natural language processing and language modeling. So, so it's really it's cool to see that these architectures are actually making breakthroughs in the last few years. And the reason why there is the word neural in this word in the neural networks name is the fact that they're biologically inspired from the human brain. So although we don't know, like there's a lot of unknown things about the human brain, we have some estimates about how many neurons are there in the brain. So there is actually an astronomical number of neurons. And there are some studies that have shown that these neurons are connected to each other, where each neuron can send a signal to other neurons. So, so that's the kind of knowledge that we have inspired scientists in the past to develop architectures that are kind of inspired from the human brain. And I wanted here to give you a simplified model of an artificial brain that could be used to a real world task. Okay, so let's imagine, for instance, that we want to predict the probability like of a certain phone is to be a top seller in the market. So I could imagine something that's very simple. So I have to predict that I could have two different inputs. For instance, the price of that phone and also the brand of that phone. So that could be iPhone, Samsung, or any other brand. And then here I have two different parameters that I will use to multiply the value, for instance, of the price, plus another parameter times the value of the brand, plus another shifting parameter that's called the bias. And once I have computed that, then I could apply what's called a nonlinear function, which is, for example, here could be chosen as what's called a sigmoid function or the logistic function. So you'll have a chance later to learn more about these functions. Then once you apply this, we get the output y, which is what we want to be the probability of this phone to be a top seller. So if I imagine something that's simple like this, where this parameter W1 is let's say -1/100. Okay, so minus here just means that the pricier the phone, the less probable it's going to be a top seller. And 1 here, so this W2 is a coefficient that we multiply with the brand in such a way that it's positive. That's because the better the brand, the more likely that's the phone is going to be a top seller. So if I do this here, if I do the math, then if I compute, for instance, like 1/1000 times 500 for the price in any currency, this is just for the sake of illustration. And then here 1 times 1. So B here is just 0. And then once I apply this nonlinear activation function, then if I check the output here, then I should get 0.5, which means that if I check this logistic function, then I am somewhere here. So this is 0, okay? So 0.5 is here. So I should be somewhere here, okay? So this is 0.5, so it should be a probability that's bigger than 0.5, okay? Or 50%. Now if I do
Hello,
the
sir.
other model, yeah, please go ahead.
It is negative 0.5 or because of the minus.
Can you say that again? Yeah. Well,
Is the minus in front of the 1/1000? Won't it affect the result that we had? Yes. Is it not going to affect the 0.5 to be negative 0.5?
The plot.
Yeah,
sorry. I'm saying that the negative sign isn't going to affect the result that we had in the bracket, which is the 0.5.
Yeah, that's right. Yeah. So I guess if we're doing the math here, that's negative 0.5 plus 1. That's 0.5. Is that like what you're referring to or something different?
Yes, please. That's what I'm referring to.
Yeah.
Okay.
So,
Okay. Yes. I get it. Thank you.
That makes sense. Yeah.
Sounds good. So this is just an example. What I wanted to say here is that this output here, so the Y that we're getting here, is bigger than 0.5. Now, if I do the other math here, then that would give me negative 1/1000 plus times 250. So that's for the second phone. And then the brand of that phone is not good. Let's imagine just something that's not known. So that's 1 times 0 plus 0. And that should give me a negative number. So that's actually negative 0.25. So if I do that on the plot here, then that should give me something that's negative, like less than 0.5 for the probability, okay? So this is one model that's kind of predicting that although this phone is pricier than this phone, the brand is better than this brand. It's actually predicting that this phone, for instance, let's say an iPhone that's typically pricier, would be probably like a better seller compared to a less pricier phone. But this is far from being a perfect model because some other people would maybe check that feature that is less pricier to get that phone. Okay? That's why we could also connect different artificial neurons to build a more sophisticated model. So for instance, we could build a probability of getting like a top seller phone. That could be based on different other factors. For instance, the awareness of different people, like of the population of this phone, the affordability of that phone, whether it's pricier or not, and also the technical specs. So that's also something to consider. And these kind of features could be also based on other kinds of features. So for instance, the price, so that's something that would connect with affordability. There is also like the awareness would be, so that's something you would see here. So if we want to connect these features with these other features, the price would go here for the affordability, and also the shipping costs would go for affordability. If you want to also when we'll talk about awareness, that will be, for instance, affected by the brand of that phone. And if you also want to check how technical specs is also affected by other factors, we could see the speed, and also, for instance, the quality of the camera. So those are factors that would affect the technical specs. So in this example, you see some sort of a notion of a layer. So here, this is the input layer where we have this data. Then what we do is we process this information to get
Hello.
these other
Uh,
sets. Yeah, please go ahead.
It looks like the screen has swapped. We are seeing your face much bigger than the screen we are supposed to see, please.
So now, can you see my tablet, like with what I'm writing here? No?
Yeah, that one has become smaller.
Oh, it became
I
smaller.
think you should check your end because my end
Yeah, I
is
think
fine.
it's on your end. Yeah.
Thank you. Thank you.
Is it fine for
I'm
everyone?
okay now. It's fine for me now.
Okay, well, thank you for checking. Appreciate it. Okay. Okay, so what I was saying here is that we have a notion of what's called a layer, where we have an input layer here. And then what we do is we process these kind of information using these artificial neurons into other sets of neurons, which we can call this like a hidden layer, which will process them further to get to the output neuron, which will give us the probability of that phone to be a top setter. So that's one example where we could use a network of neurons to predict something that we're interested in a real life example. And this example also shows the notion of activation. So this is something you'll see a lot in machine learning, where you see that this, for instance, this neuron and this neuron will fire here to activate this neuron here, which is related to affordability. For instance, here, this neuron will fire, and this neuron will fire this neuron to activate information about technical specs. So even though this is biologically inspired, it's also being used in the context of machine learning as a name of activations. And in the context of machine learning, for instance, in the context of feed-forward neural networks, we have a similar structure where instead of having some weights that already predefined, like here in this example, we allow for these weights to be trained, to be learned. So we don't actually define these connections. So those are learnable connections between different neurons. And one typical thing we have here is that the neurons are fully connected to all the other neurons in the layer. So for instance, in the input layer and the hidden layer here, the neurons are fully connected to each other. And the reason why we have these, this hidden layer, is to allow for the model to be more complicated and to allow to be able to predict the things that we're interested in without having to do feature engineering. So going back to that example of predicting the phone is a top seller, we wouldn't know what are these features in advance. Like, it would be good for the machine learning to learn about these features through these connections that we will learn in the training process. So here I kind of give you an example for how what these features would look like, these intermediate features would look like, but in a real world application, we want these features to be learnable by the algorithm during the training process. So this would allow to avoid us to do feature engineering or to minimize the human feedback during the training process. So one example of a case where we kind of don't have this hidden layer is in the context of what's called logistic regression. So we will get to that in the demo that I will do in a second. So you will see that this model is not very expressive compared to that one where we have more connections and more complicated, more expressivity.
Hello?
Yeah, please go ahead.
I heard that these intermediate features, sometimes they can be quite complicated. They have limited interpretability for us at times. I was wondering if there is a way to kind of analyze those features just before they get passed to the output side.
Yeah, very good question. Yeah. So the kind of one of the downsides of deep learning, like a lot of tools in machine learning is the fact that they're kind of like block boxes. They're not interpretable. So there's actually an area of research in machine learning called interpretable machine learning. So a lot of researchers are working on that. So I would encourage you to check out like papers that are in this field. So there are some people working on that, and it's an ongoing area of research. This is a really great question. Yeah. I guess at
Thank
this
you.
point, like the way it's presented now, they're not interpretable. Sometimes, as you said, it's hard to interpret what's their features. It's just that in this example, I kind of simplified a lot, but I guess in real life, we don't know what are these features. We're not supposed to know, since like what we're interested in the most is this outputs at the end that we're interested in. And
Okay, thank you.
Does that answer your question?
Yes, that's pretty okay.
Okay, thank you. Okay, so also commenting a bit on the feed-forward neural network, we have this notion of the layer that I've talked about. So this first layer is called layer 0, or the input layer. We also have intermediate layers. So this is, for instance, layer 1, layer 2. Those are called hidden layers. They're in the middle between the input and also the output layer, which is the last layer. So that's, for instance, layer 3. And what's special about these feed-forward neural networks is that they can be very deep. So instead of having only 3 hidden layers, you could imagine having many, many, many hidden layers. They can even reach hundreds of layers. And that's also one reason why you hear about deep learning, because it requires having deep architectures that can learn very, very complicated features about the data you're interested in. So just to simplify that, I would just want to touch upon the question that was highlighted before about how we could like map a picture of handwritten digits to a label. So I'm going to do this through this example of cats and dogs, but the principle would be the same. So here, let's imagine that we're interested in classifying pictures of cats and dogs using the feed-forward neural network. So what we need to have is to get a lot of pictures, or sort of a data sets. So I need a lot of pictures of cats and also a lot of pictures of dogs with a corresponding label. So for instance, these would have label 0 and these would have label 1. Okay, so that's one example. And here what we could do next is choose the neural network we're interested in. So we need to choose the number of layers, the number of neurons in each layer. So those are called hyperparameters that we need to play with. And then for the input layer, we need to kind of feed in each pixel of the picture to one neuron in the input layer. So that will be the first pixel, second pixel, third pixel, and so on until we reach the last pixel, which will be fed to the last neuron in the input layer. And then that's processed through these connections to the hidden layers until we get to the output, where we either get this neuron fired, which is not the case. Like we expect that's this neuron to be fired the most if we have a picture of a dog. So to be able to do this, we train the neural network to like on several examples. In the ultimate hope is that we want these hidden layers to learn about features of the picture. So for instance, we hope that the first hidden layer would learn about the smaller features like the ears and the eyes and the mouth and also feet here. And this other additional hidden layer to learn about like the bigger picture, like the face and also the feet here, so that we will be able to predict the correct feature, or the correct label, which is dog here. So to do this, we need to, yeah, please go ahead.
So please, can you explain what the layers are? Are they like functions that get activated by the input data, or something like that?
Yeah, so roughly speaking, so the layers, for instance, the hidden layer is made of a bunch of neurons, where each neuron is just a real number, right? And the real number is computed out of the value of the previous layers, of the previous neurons in the previous layer. Okay. I haven't talked about the math yet. I'm just talking about the high level idea, but does that answer your question?
Yeah. I'm okay. Thank you
Okay,
very much.
thank you. Now in terms of training or teaching the neural network, what is a picture of a cat or a dog? What we need to do is feed in that picture to the feed-forward neural network. So initially we might get the wrong answer. For instance, here we might get these bunch of neurons fired and then these bunch of neurons fired until we get this neuron fired, which corresponds to a cat. So that's not the correct answer. What we want is to teach the neural network in such a way that the next time we feed in the picture of a cat, we get instead a dog, which is the correct label. So to do this, we use a notion called backpropagation. So that's a technical term in machine learning, where the idea is we want to backpropagate the error back in from the outputs to the input layer. So we propagate the error here, and here there's maybe an error here, maybe an error here, an error here, until next time. So we do this many times until next time when we ask the neural network again, is this a cat or a dog? Then hopefully once we feed it this picture again, then hopefully we get the correct label. Okay, so this is all high level explanations. Of course, it will be good to check out the math. So before I don't think we will have time to cover the math in this session. So hopefully we'll do that in the next lecture next week. But what I wanted to show you now is just a demo for if you want to practice the notions we've seen today. So that's on a website called Playground TensorFlow, where you can train neural networks on your browser. You don't need to use your laptop to train. So we will do that now. So let me share my other screen. Okay, so are you able to see my browser here? Are you able to see like this
Yes, we can see.
page? Yeah.
Yes, we can see.
Cool. So here I wanted to show you this website, which is pretty cool. Like you can actually play with neural networks, feed-forward neural networks. So I would encourage you to practice here. So you can add hidden layers. You could also increase the number of neurons in each hidden layer. So I would encourage you to try that. But first, I want to try like this data set, which is made of orange dots and blue dots. So you can imagine that you could separate them by a line. And if you try like this simple neural network, which is also known as logistic regression, if we start training, so this is using this learning rates, which hopefully we'll get to in next week, and then using this sigmoid activation function at the outputs. And if we do this classification task, then you see that the network is able to perfectly separate between blue dots and orange dots. Okay, so it draws a line between the two. Okay, but now if I imagine something that's a bit complicated, if I restart and use another data set, so that's on this left side here, I can choose this other data set where I have blue data points here and here in the corners, and also orange data points on the other corners. So you can see that it's impossible to separate the data sets with a line. So you need something that's nonlinear to separate it. So even if you use this simple architecture, you'll see that it's not doing okay. So for instance, here you see that it's drawing a line here, which is not good to separate between the two sets of data points. So if we try something different, if we try to add one hidden layer, and to add a bunch of neurons, then if we do this again, if we train now, then you're starting to see that it's actually drawing some nonlinear boundaries between the lines. And I just wanted to show you this example to highlight the importance of adding hidden layers when you have something that's complicated, like where you need to draw these nonlinear boundaries. So I would encourage you to try that after this session today. And please feel free to send me your questions later. But I guess since we don't have time to cover the math, I guess I would do that next lecture. So we'll talk to you about all the math that we've seen, just a translation in terms of mathematical equations of what we've seen today. And then we'll also cover the application to classification of phases of matter. Okay. So with that being said, so in the next hour, I guess we'll take a break, few minutes break, and then we will go to this collab, which is provided to you, I guess, on a PDF. So you'll find a link to this collab. So I guess you'll all need a Gmail account to be able to access this collab. So basically what this collab means is that it will allow you to run Python code on your browser without having to run that on your laptop. Okay, so I would encourage you, like after the maybe 5 minutes break, to read like the questions and also to do the exercises. So I'll explain after the 5 minutes break what you're supposed to do, but that's what we're going to do after the 5 minutes break. Okay. In the meantime, if anyone wanna take some break, and then you're welcome to. But if you want to stay here, I'm happy to take your questions before we get started in about 5 minutes. Okay. Thank you, everyone. Okay, so we'll stay here for a few minutes, and then if anyone has a question, please feel free to unmute. Thank you for your kind comments. Yeah, there was a question on the chat on the code. Yeah, so let me share also. Yeah, let me try to share the code with you here, because I guess, yeah, maybe not everyone has access to the PDF. I shared with you, so let me give you the code here. So you'll find that on the chat. Okay, so once you click on that link that I just shared on the chat, you'll be able to access the code on Google Colab. Please let me know if you didn't manage to access that. I'll try to another solution to figure it out. Okay, but I would encourage anyone to try to go to the link and then to see if it works for you. If it doesn't, then please write me on the chat or just unmute yourself, and hopefully we'll figure a solution. So there was a question on the chat: for the neural network, do you need to add another layer in case the output is incorrect? So that's a great question. So what we do typically is we fix the architecture before the training. So we choose a number of layers, and then we train, and then hopefully if we don't get good outputs, like meaning that if the labels or if the predictions don't match the labels, then we try a different architecture. We try to increase the number of hidden neurons, or we try more layers. So that's what typically done. In terms of the second part, like what do you add to get the correct outputs without backpropagation? This is a great point. Like I guess I've seen a lot of applications where you need to retrain the whole thing. If you design a new architecture, if you like change the number of neurons or number of layers, you do the backpropagation on the whole thing. But I've seen also other applications where you keep the old network and then you add one network while preserving the old parameters. So sometimes called transfer learning, or has different variations where you kind of keep the old parameters and add one trainable layer to increase expressivity. So this is a great question. I hope that answers your question, the first question. The second one, so the question is like whether deep learnings are inherently better or shallow networks are enough for some kind of work. This is a great question. What I would like to mention is that shallow neural networks, or networks within inputs and outputs, are actually applicable to a wide range of tasks. I guess like my message here is that you should try shallow neural networks first. And then if they don't work, then that's a good time to try deeper neural networks. So the answer is that like you shouldn't start right away with deep learning models. It's good to start with the simpler models. And then it's like the physicist approach. Like you always want to start simple and then make things more complicated if needed. Okay, so that's the main message here. I hope that answers the second question. Okay. If there's no other question, now let me share again my screen. And so hopefully, I hope everyone now can see the Colab. So if you didn't have access, I encourage you to check out the link, either on the PDF or on the Zoom chat, and you should be able to see something like this. If you see this, then I would encourage you to use Save a Copy in Drive. Okay, so the link on the link I shared, you won't be able to modify it because you only have the view access. So you should click here on Save a Copy in Drive, and you will be able to use your own accounts to modify the code here. So you should get something like copy of that, okay? And then what I would also encourage you to do is changing go in here to the runtime and change runtime and make sure that you're using a GPU, okay, instead of a CPU. So GPU is if for those who are not like familiar with this terminology, it stands for graphical processing unit, which stands for a compute hardware that allows to like doing computations much faster compared to the CPU. So always like opt for GPUs if you can compared to CPUs. You can also compare if you're curious to see what's the speed, but just try the GPU so you can just click on GPU here and save. Okay, so once you do this, then so here I just shared some few notes that you can read, but the main goal of this tutorial is to use feed-forward neural networks to classify these spirals. So here I have a data set which has three, like for instance, in this picture, it has three different classes. So there is a yellow, there's a purple, and there's a green. And I want to use a neural network to classify these three spirals. So that's one example of supervised learning with classification. So here I have three branches, and each data point is two-dimensional. Okay, so in the first example I gave in the lecture, I only have one dimensional, like one real number and one real number for the label. Here, the data point is two-dimensional, so I have the x-axis and the y-axis, so I have x1 and x2. And the labels, I could have a discrete number. So since I have three branches, I could have 0, 1, or 2 for the label. Okay, so that's for the example here. And one way of also representing that label is through this so-called one-hot encoding that I briefly mentioned in lecture. So instead of using 0, we could use 1, 0, 0, or for 1, we could use 0, 1, 0, or 2, we could use the vector notation 0, 0, 1. So there's a question in the bottom of this tutorial asking you, why do you think this is a good representation? So try to think about it once you get to that question. But I will share the solutions later, hopefully, after the end of this tutorial, okay? And then after going through the introduction, you can start with these questions. So for instance, I can do the first question with you. So the question here is about running the code and making sure that it works and making sure that it does actually a poor job at classifying the data. So the thing is that this first part is about generating the data. So if I run the code and I could just click here to run it. So now it's connected to the GPU and it should run in about a few seconds. Okay, so let's just wait to get started. In the meantime, you could also do the same thing with me. Okay, so you should see something like this. So it's running. At this point, like you don't need to check the content of this code, but if you're interested to understand, like if you're still getting started in Python, I would think if you're not understanding what's going on, like I would encourage you to use this AI tool here. So it's called Gemini. And if you don't understand a certain thing, like it's in a certain line, you could just copy it here. And you could say, what's going on here? And then you could copy the line. Oh, sorry. I should have copied this one. And then it should be able to explain the commands. So you say that line initializes a numpy array with zeros. Okay, so it's a way of using zeros. So I would encourage you to use these tools if you don't understand something in the code. Okay, so I'll trust you to use this tool to help you understand the code. But I guess at this point you can just run the code. So the first part of the code should give you the spirals. So you should get 3 spirals. And then here, this is about defining the feed-forward neural network. So this is based on what's called PyTorch. So it's a machine learning library. There are different libraries. There's PyTorch, there's TensorFlow, and there's JAX. Like, so this is only one choice, but I guess you could also use other libraries. So we can import PyTorch using import torch here. So it's already installed in Google Colab. You don't need to install anything. So here we have 2 different layers. We have the inputs and the output layer. So those are the sizes that are defined here. We also define a linear layer that's transforming the input to the output. And we also define a set of different activation functions. So this is something I didn't have a chance to explain in the lecture, but hopefully we'll get to that next time we meet. So I'll just encourage you to try, and also you could also ask Gemini, what's this activation at this point? And here, this is like the way it's defined. So we do a linear transformation of the inputs, and then once we do this, we also apply this sigmoid activation to get to the outputs, which is returned here. Okay, so that's a simple input to output linear network. Neural network that we've seen here without a hidden layer. So that's basically what was referring to 2-dimensional inputs to, like, instead of a 1-dimensional input, it's a 2-dimensional, a 3-dimensional output, which corresponds to the label. Okay, so I encourage you to check out this code here, and we'll get to the optimizer and to the cost function later. So if you're not sure about what to change here, let me know and I'll be happy to help. And there's the final part, which is about training the architecture. So there's a for loop here, which is basically trains the architecture in many iterations until you get to the final, until you satisfy all the conversion steps, all the required number of training steps. So I would encourage you to try to run this cell and also the other cell. So let me do this here. And then hopefully you should see something like this, where this simple neural network is not able to classify the different spirals. And you can see it's similar to that network here. It's separating, like it's using linear boundaries to separate these spirals, which is not ideal. So one of the questions is to use like a hidden layer, to include a hidden layer to be able to better classify these spirals. Okay, so this is a bit of introduction here, but I would let you just read through the introduction and the questions, and if there are any question, I'll be happy to answer. So I'll just be watching from here, and I'll be happy to help anyone. You could also share your screen if you want to, if you have a question somewhere, and I'll be happy to help you. Okay, so feel free to structure this tutorial section based on your interests. In the meantime, you could also ask me questions while your colleagues are working on on the tutorial. Okay, thanks everyone. Yeah, so that's so there's a question in the chat. How can I determine the optimal number of neurons? This is in the hidden layer. So this is a great question. In priori, we don't know what's the optimal number of neurons. It's more like it's more about experimenting with different number of neurons so that we can find the answer that provides the best prediction that matches the labels. So sometimes, so this is one of the questions that you are asked, like to see how the accuracy like is affected by the number of neurons in the hidden layer. So I would encourage you to try this question, like once you finish all the other questions, and to see how that affects the accuracy. So this is something that would help you to answer your question. But I mean, the simple answer is that we don't know a priori. We need to do experiments to find the optimal number. Oh, great question.
Hello.
Yeah, please go ahead. Yeah.
Yeah, please. Would you recommend us to use something like an algorithm to determine the optimal number of neurons? Like, say, beyond this case, is it generally recommended to do something like that? Something like maybe Bayesian optimization to find the optimal number of neurons?
Yeah, this is, it's great you refer to Bayesian optimization. There is this package called Optuna. So this is one example of one package you could use. It allows to automate this hyperparameter search. So the number of neurons is one hyperparameter, and you could include it in your code. So you find examples here. So I'd encourage you to use that if you find it relevant. But if you just have few kind of tweaks that you can make, you can do it by hand without having to use like these kind of advanced tools. But if you have a big application where you have plenty of possibilities to try, you can always try these kind of tools. No, great suggestion.
Thank you very much. I didn't know about Optuna.
Yeah, I guess, please try, you could always try that. I mean, it was very helpful in one of my research projects a few years ago. So yeah, you can definitely try it. There was a question in the chat on like codes, like so the Colab doesn't have Python code. Oh, you can't find the Python code. Maybe if you want, you can share your screen, or I'm not sure if you can do that. So let me stop sharing.
I'm doing it on now. If you can see.
Yeah, so that's good. Like I guess you can go down. You're able to go down a bit. If you want to, you can scroll down more. I guess if you scroll down a bit more. Yeah, even more. It's actually below the question. Yeah. So there you'll be able to find that code. Yeah. Does that?
Yeah. That's cool. Thank you.
Okay, it's a pleasure. Yeah. Okay. Okay, you're not expected to do all the questions. Just try what you can, and I'll share the solutions with you later. Okay. And I guess some of the things here are also like something we haven't done, like activation functions and ReLU. I guess you can either ask Gemini here if you want, like what is ReLU? Like if something you don't know, you can always ask this AI tool. Or I can also just send me a question and I'll be happy to help. So here it provides a definition. I can always help you out if this tool hasn't provided a satisfactory answer. Okay. So just one question I could ask to anyone, like did anyone struggle with running the code? Are you all okay? Like did you manage to run the code first?
Hello, Mohamed.
Yeah, please go ahead.
Yeah, I think I was able to run the code using the Google Colab, but I tried Jupyter Notes. I was able to run it there, but I was trying to run it using the Jupyter notebook, but it wasn't working.
Yeah, this is a great question. The thing is, like in Google Colab, you already have these packages installed. So like NumPy, Matplotlib, and for instance, Torch, they're already installed in the back end of Google, like GPUs. But if you do that on your laptop, you need to install these packages. So it will take a long time. So I would recommend you to use Google Colab at this point. But I guess if you're interested to run things on your laptop later, you can always look online for how you could install these packages like PyTorch or NumPy. That would help you to run like things on your laptop.
Yeah, hello, Mohamed. I think I did install some packages with the touch, but then there was something that was missing.
Yeah.
The touch n.nn.network, the neural network.
Oh,
If
that
I could
part
share
here?
my screen. Exactly. That one, this one cannot be identified. Yes, that part
Okay.
wasn't.
Yeah, if these kind of things happen, like you can always like it's hard to find the issue where the issue is coming from, but you can always ask ChatGPT or this kind of tool, like, was that the issue? Like, was not in the identified? Was that the issue? Like that? Like when as I'm writing here?
Okay, let me go. I'm checking my.
Sure.
Okay.
Yeah.
Because
sometimes, yeah, it's even like I also
yeah,
struggle with these
the
kind of
error
words.
okay. I think that I had two different errors, so I have to
Yeah.
install that, and then there was another error that talks about no model name. Touch
Oh,
dot
no.
underscore prims underscore common. So the model name was not identified.
Oh, okay. No more than, yeah, this one, this model.
Yes.
And have you ran this cell? Like, did you run this cell before? Like when you did this on your laptop?
I think yes, I ran this. Everything was together, so I have to run
Oh, you
everything.
ran everything. Okay.
Yeah. It was only when I used Jupyter Notebook, it was only the first part that I was able to run, but the others couldn't run, so I was able to get
So
the
no,
first aspect.
like so on Colab everything worked?
Yes.
Okay. So maybe like I would advise you to use Colab for now. And for later, I guess like since it's hard to you can either write to me like later after the session, we could figure it out.
Okay. Thank you so
Or
much.
you could copy the error in Gemini or ChatGPT. Hopefully you'll get some directions. I use that a lot when I get debugging errors. Like it's even challenging for me sometimes to get an error. So if you're comfortable, like you can use the Colab here, and I'll be happy to help later if you want to work on your laptop.
The solution. I'll get that. Okay. I'll do that. Thank you so much.
It's a pleasure. Thank you. Okay, so I'll share the solutions to exercises 2 and 3 in about 10 minutes so that you'll be able to move forward with the other questions, okay? In 10 minutes, if anyone has an answer, I mean, you'll be happy, like, you'll be welcome to share. If there's no one proposing a solution, then I'll share my own solutions. There was like a very good question, like what's the difference between cost and loss function? They're actually the same, it's just different namings, like conventions. So loss function, cost function, they're the same, they stand for the same thing. And the backpropagation actually used that. So since I didn't have time to cover that in the lecture today, I was planning to cover that. I'll plan to cover that next week, but just as a quick answer to your question, the cost function is basically a way to quantify the error between the prediction of the neural network and the true label. So when you have a cost function, like when you have a label, the prediction matching the label, then the cost function should be as low as possible. For instance, if you have this, what's called the mean squared error, the difference between label, the correct label and the prediction of the neural network, the difference should be 0. Okay, so basically this information is used to backpropagate the error through the network. Okay, but I hope that answers the final question on the chat. Yeah, I see one hand. Yeah, I see one hand raised. Yeah, please go ahead.
Yeah, I was just about to, like, I found like a solution. I've tried it out, and I thought you were to share our screens or something.
Yeah, this is great. I mean, yeah, just wait until we like in 7 minutes or so.
Oh,
And
okay. Sorry.
once
Okay.
once we are at this point, yeah, you're welcome to share your screen to share with the participants if you want. But
Okay.
it's great that you managed to do the exercise 2 and 3. You can now go to the other exercises. And once the time comes, then would encourage you to raise your hand and to share your screen.
Oh, okay.
Thank
I
you.
was really intrigued by the plots, how I don't know if there's a bit of uncertainty that is used to determine the boundaries. I was just trying to understand the code a bit.
Yeah.
Um,
So are you talking about these boundaries?
yeah, the boundaries. I'm really interested in how they were generated. I don't know
Yeah.
if the,
Yeah, so it's actually part of this grid here. So there is this generate coordinates covering the whole plane. So it's actually that code here. So this code generates the grid, like the 2D grid.
okay.
And then basically you get all the inputs from that grid, and then you that's this torch input, and then you feed that through the model to get the predictions. And then you generate the predicted classes. And based on the predicted classes, then you print the predicted classes. So this will give you different colors based on the predicted class. You see here this counter RF, counter F, plt.counter F will give you that.
Oh, okay. Okay. I thought they were very interesting. I thought they were uncertainty boundaries for.
Oh, no. So these are actually the predictions. So this region here, this means that the neural network is saying this region should be yellow, and this region should be green, and this region should be purple. But it's not here. You see, like these yellow dots are misclassified.
Yeah, misclass. Okay. I tried changing up the neurons a bit, and I saw that the lines distorted significantly.
Yeah, this is exactly the same thing as here. You see, like when you do this here, you're kind of gets distorted or nonlinear boundaries. Well, let me try this again here. You see like these nonlinear boundaries for this example. It's a similar observation as well for Disco.
Oh, okay.
Thank you for sharing.
Yeah. It's really nice code.
Thank you.
Hello, bro, please, can you hear me?
Yeah, I can
hear everything. Okay, please, looking at the final training cost and final training accuracy, please, are we looking at a particular range to actually determine if your training is doing well? Like here we have like for accuracy we have 0.48. Should we consider a range? Could that change?
That's a very good question. Yeah. So the accuracy should be as close as possible to 1, like 100% accuracy. Ideally it's not 100%, it's like 90% or 95%. So that's what we should be aiming for, like in the higher percentages. The training cost, it should be also as low as possible. For instance, when we are using this mean squared error, it's as close as it should be as close as possible to 0. Here it's 0.16, which means that there are some errors which are highlighted by these misclassifications. For instance, there's yellow dots, there's green dots here. So I guess when you will introduce this hidden layer, you'll see that this training constant will be lower and the accuracy will also increase. So does that answer your question, Moses?
Yes, please. Thank you very much, bro.
It's a pleasure. Thank you. Okay, so we will do the solutions to exercises 2 and 3 in about a minute. So okay, if you have any questions, let me know. Yeah, so what I meant by draw the neural network is like in exercises 2 and 3 is that like I want you to draw the neurons and also the connections between the neurons. So for the first neuron, it's an input and output layer, and in exercise 3, you have an input and hidden and also an output. So you should be careful about to know how many neurons in each layer and also the connectivity. So that has to be drawn in the you can do that on a piece of paper if you have. I hope that answers your question. No, it's not supposed to be good. You can just draw that on your on a piece of paper. Yeah. Yeah. So it was another question. How do you evaluate your output? That's a great question. So there is this part of the code, like you'll find it in the training part. It's over here. So once we get to the predicted class, so the neural network in output is a 3-dimensional like vector. And what we do is we get the prediction that has the highest number or the highest probability. So that will be the predicted class, which means the class that the neural network has the highest confidence. And what we do is we see whether that predicted class matches the label, which is this Y train here. And basically, if they match, basically we average over all the matches. And if we have a lot of matches, like if all of them are a match, we should get this number equal to 1. If there are a lot of mismatches, then it should get closer to 0. And if there is a mixture, we should be some number between 0 and 1. So that's for the accuracy, but we could also estimate the cost, which is given by this cost function that we have defined before here. So that's the mean squared error. I'll go over that next week, but if that doesn't answer your question, let me know. I could provide more clarifications. Hope that answers that question. Thank you. Okay. I guess now I guess it's a good time to share solutions for exercises 2 and 3. So second exercise is about drawing the neural network architecture that was already defined here. I guess I already have that, but I guess if anyone want to share their solutions for exercises 3, you're welcome to share your screen. So let me start with the exercises 2. So this is the solution. So basically, each input is 2-dimensional. So I have 2 inputs, x1 and x2. And then I have also an output, which is k-dimensional. So k is the number of branches. So since I have 3 branches, then the output should have we should have 3 outputs. And we have also full connectivity. So we have this neuron is connected to x1 and x2. Same thing for A2 is connected to x1 and x2, and also for instance, A3 connected to x1 and x2. But it doesn't have to be only three branches. We could also have 5 branches, 10 branches. So that's a parameter you can actually tune here in the beginning of the code. So if you go here, k is equal to 3, and the number of data points is also 50 per branch, so you can tune that. If you want to increase the number of branches or decrease, you can tune that number k. Okay. So I hope that answers that first, this exercise 2. Now, there's also this exercise 3, which is about adding a hidden layer with 4 neurons in this architecture. So basically, this neuron would look something like this. So all we did is basically we inserted a hidden layer in the middle. So this layer and this layer is the same, but we inserted a new hidden layer with 4 neurons, as you see in purple here, where we have also full connectivity to the neurons in the input layer and also in the output layer. Okay. So the question now is how to do that on the code. So if anyone is interested to share those solutions, let me know.
Yeah.
Yeah, please go ahead. Yeah.
Yeah, let me just share my screen.
Yeah, please go ahead. Yeah.
Uh, can anybody see my screen?
Yeah, I can see your screen. Yes.
Which is it?
Yes,
The code
please.
screen? Code screen, right?
Yeah, this is the code screen. Yes.
Okay, okay. All right. So I made the changes just here. Just
Very
insert
good.
a bunch of linear layers, and then I wasn't too sure if I inserted four exactly because this is a matrix input, and then the output size. I know it was three, so I just three, and then I added a four, so a 3 by 4 matrix. I think I added about 12 neurons instead of four.
Yeah.
I
So
was
what you did first,
experimenting.
yeah, that's good. So what you did, you computed linear one out, which is self-linear one. Okay. And then you applied ReLU, right? And then you applied another layer, we call it self.linear, which maps the outputs to like a hidden layer of 4. Okay, so what you did basically is like you have the input and the output, and you added the hidden layer after the outputs.
Well, not.
Yeah.
I sort of just take this as a number. So this output size 3. So 3, and then I just took it as a number because I knew that this is the output size. It's supposed to be the one hot 3 encoding. So what comes out should be a 3 outputs, and then that just passes to the output variable, and then you return the output layer.
That's a good like it's great that you like kind of define new linear layers. So basically what you have is a network with size 2, and then you also have a hidden layer with size 3, and then also a hidden layer with size 4, and then you map that again to size 3. So you have 2 hidden layers in one input and one output.
Yeah.
No, but
I was
it's
just
great. Yeah.
I was just tinkering with it at first just to see I was excited with how the output kind of looks like every time you train the model. I can see that the accuracy improved a little bit more compared to the first time.
Yeah, can you show your so it seems that you're getting this nonlinear boundaries. That's good. And you see the accuracy is also increasing. That's good. So it's getting beyond for like 48%. So you're now 78%.
Yeah, now I think this is the best I've had since I tried. I've been trying it a couple of times, and I think this is
good. Cool.
Yeah.
Nice. Thank you. Thanks very much for sharing. Yeah. So if I may, let me also share my screen to show you the solutions that I have for you. So let me run this code here. I guess I have also to terminate this session. Somehow Google doesn't allow to get multiple GPUs, so I guess I'm allowed only to use one. So let me run this code just to show you a demo. But what I did here is I commented the old code. Okay, so this is the old definition of the feed-forward neural network. And I defined this this new linear layer. So it's somehow similar, but not quite the same, in a sense that what I did is I defined this new variable, like or attributes, self.hidden size. So initially it was self input to self output, but now I need something in the middle. So I need to insert this, like this size in the middle. So that's what I did here. I defined a new, like an additional linear layer where the input now is self.hidden size, and the output is the size of the labels. Okay. So here instead of so what I did here is you applied the linear transformation on the inputs, and then you could either use sigmoid or ReLU. Let me just stick with the sigmoid that we have in the old code. And then once we do this, once we get the activations at the hidden layer, then we could add another transformation, which maps now the hidden to the outputs. And then once we do this, we could use another activation function called softmax. So let me comment it out and just use sigmoid until we explain softmax later, since I didn't have a chance to explain it. So just make sure we do things we covered today. Let's use sigmoid at the outputs. So once we have that output, then that's something we will return as an output of the network. Okay, so this is the hidden size for, and then that's the way we're gonna define our feed-forward neural network. Okay, so once we have that, then we should be able to train. And okay, so as you might notice, like you see these nonlinear boundaries, and you see that the training accuracy is increasing, and also the training cost is going below what we have for the other architecture. Okay. So this is the result here. We could either like add more training steps. So here the number of epochs is 10,000, but we could also do 50,000. Let me do the training again. Okay, so this should train for longer. So the more you train, I guess, the better the better accuracy, since you'll have more time to backpropagate the errors and to correct the connections in between the neurons. So here you see some sort of saturation. Now it's a bit increasing. Okay, so you should, yeah, so now it's getting to 80%. Okay. So I would encourage you to try like also changing the number of neurons in the hidden layer. So that will come also in the following questions. I would also encourage you to try to use different optimizers. So there's this optimizer called Adam optimizer. So if we have a chance next week, we'll cover that. If not, be happy to talk about it later. So this is like a very powerful optimizer that will allow you to train a neural network. And if you use that, you should be able to see like to get a better performance. See here, you see like a very quick improvement to larger accuracy. See like we're close to 90% accuracy. So I would encourage you to try to play with different hyperparameters and different optimizers, different cost functions. So if you're not sure about how to do that, just wait for next week before to cover more material. Hopefully that would help to understand more details about what's going on in the code here. And it's okay to, if you don't understand everything about the code, just keep trying and also asking for clarifications from this AI tool that should be able to clarify some ambiguities here in the code. Okay. But in the meantime, I would wait from your feedback on questions. Are there any questions so far? So there was a question about how many times we train the model. So that actually depends on the number of training steps. So that's something we could change. So that could be either 10,000 steps, 50,000. That depends on the time we have for training. And sometimes like could be not a good idea. Like sometimes training for longer might not lead to better accuracy. So for instance, that's actually just happened here. So we trained for longer and then we got a drop in the accuracy. So sometimes you have to stop earlier to get a better accuracy. Okay. I hope that answers your question. Okay. Are there any questions as well? Okay, if not, then yeah, I guess we have 5 minutes or so left. You can try the other questions. If not, I would encourage you to just explore the notebook and to make note of your questions. And then next time, I'll make sure to cover those questions and also cover more material that's here. Like I have explained the learning rates and the different activation functions and the cost functions. So hopefully that will be something I will cover next time we meet. So I'll just be here for the next 5 minutes if there are questions. So please feel free to unmute and ask your questions. So maybe I'll share that solution with you. So everyone who want to do the next questions, you can actually take a look at this change here. So that's the main change. If anyone want to see that, but I will share that also with you later after the session.
The learning rate any different from I mean the learning rate is like a training process for the model, right?
Can you
So I
say
wanted
that?
to ask how many times the learning rate is like a training, how well the model is performing, how well it's identifying the patterns in the data is given. So I wanted to ask, when you are training the model for a couple of times, the performance of the model keeps reducing. So how do you account for that?
Oh, so you're saying like sometimes when you're training for more, you get a reduction in the performance?
Yeah.
Yeah, so that's sometimes called, there's a technical term for this called overfitting. Like sometimes training for more, it's not good. So if you want to account for this, maybe what you could do is like stop earlier. So there's a technical term for this called early stopping. That helps to kind of deal with this issue of a reduction in the accuracy when you train for more. Does that answer your question?
Yes, please. Thank you.
Oh, it's a pleasure. Yeah. There was a question is like, how did it take you to write the code? No, I would say a lot of like many days. Yeah, so that code took a while to write. I guess like it's not easy to write things from scratch, like in 1 hour or something. Like this code was like mainly used for like pedagogical purposes. So like just don't be afraid. Like it's okay. Like if you feel like this is like a big code with a lot of details. It's done on purpose just to give you something that's ready for you to experiment with. If you're interested to getting something from scratch, I guess that will be even a project on its own. Like it would take a while. Like so, if you're interested in getting things from scratch, you're welcome to study the code and to do that on your own. But I guess yeah, don't be. It's okay. Like this is something that took many days to work on and to debug and to figure out uh, how how it will work properly. Yeah. Thank you for the question. Yeah, how do you incorporate multi-layer perceptron and Bayesian optimization into the model? So first of all, like maybe I should define for your colleagues what's a multi-layer perceptron. So a perceptron model is a model in such a way that these kind of nonlinear activation functions are not applied. So you only have linear activation. I guess that's my understanding, or unless you have some other special activation functions. I guess we're not doing that here. So the neural network, feed-forward neural network is a generalized version of this multi-layer perceptron in the sense that we use these nonlinearities. You could either use a sigmoid or any other one node activation function. So we'll cover that next week. Don't worry about that. And Bayesian optimization, so we are not incorporating that here. We're just specifying the hyperparameters. We're fixing the architecture, and then we're training using a fixed set of hyperparameters. I guess Bayesian optimization would help you to find the optimal sets of hyperparameters. So that's why we're recommended using these kind of tools like Optuna. So you might find other tools out there in the literature, but this is one tool I've used and that worked very well to automate the process of hyperparameter search. Okay, I hope that answers this question. Okay, but if not, I guess I guess your time is 6 p.m. So I guess I don't want to take more time for this session. Like maybe some people would need to go. So thank you everyone for your kind attention, and it was a real pleasure to be here. And I look forward to coming back here next week. So next time, I guess we'll get started instead of 4 p.m. GMT, we'll start at 5 p.m. GMT. So I just want to highlight this change of time, but I would I'd love to meet with you again next week. And please feel free to send me your questions by email. Yeah, you feel free to use my email. I guess you could ask Henry for my email, and you can ask me questions later. Okay. Thanks very much again. And it was a pleasure to meet you today. And I look forward to meeting you next week. Thank you.
Okay. Thank you very much, Mohamed. So thank you everyone for your attention during the session. And I also like to pass on a special thank you to Mohamed for delivering an insightful lecture on the basis of neural network and neural network in PyTorch. So next we will continue by diving deeper into the neural networks and their application in physics next week, as he has already said. So you shouldn't forget to practice and the concept that we covered today to reinforce your understanding. Also, the video will be uploaded to our YouTube channel shortly. So within the week, you will have the video on our YouTube channel. And I guess you already have the notebook, so you can keep on practicing with that. So thank you all for participation, and we look forward to seeing you on our next lecture, which is on this Friday. Bye-bye.